Imagine we have two groups of data. Blue points belong to one class, orange points belong to another. Our goal is simple: separate these two data correctly. At first glance, this seems easy. The groups are already apart from each other. So where should we draw the dividing line? Which one is correct? Maybe this line. But this line works too. And this one also separates the data. Even this line gets every point correct. Wait a second. If all of these lines classify data correctly, then which one should we choose? This is where the machine learning becomes interesting. Our goal isn't find boundary that works. The goal is finding best possible boundary. But what does best possible actually mean? Why should one separating line be preferred over another? To answer that, we need a new idea. Suppose we choose this boundary. It separates the two classes correctly. But correct isn't enough. We want a boundary that remains reliable even when new data arrives. Look closely. There is empty space between two classes. Instead of focusing on boundary itself, let's focus on this gap. The empty region represents the safety zone. The farther the classes are from the boundary, the less sensitive the model becomes to noise and small variation. So naturally, we like this gap to be as large as possible. A larger gap means larger safety margin, and a larger safety margin usually means better generalization. The distance is called margin, and maximizing this margin is the central idea behind support vector machines. Here's the surprising part: most of these points don't actually matter. These few points closest to the boundary determine everything. Move one of these points and the boundary changes. Move points far away and almost nothing happens. These critical points are called support vectors. They support the position of the optimal boundary. Now everything starts to take shape. This line is a distant boundary. It separates the two classes perfectly. And we can write it mathematically like this. This equation represents every point that lies exactly on the boundary. But a single line is not enough, because support vectors machines don't just separate data, they build structure around the separation. On one side the boundary shifts outward, on other side it shifts in opposite direction. These two lines define the limits of the margin. And we have a region between them. Now here's the key idea. All three lines come from the same equation, same weights, same bias. Only the output value changes. 0 gives the distant boundary, plus 1 and minus 1 define the margin boundaries. So instead of thinking in terms of drawing lines, we think in terms of parameters. A weight vector controls the direction and a bias term controls the position. Together they define every possible separating line. And now something important becomes visible. Only a few points sit right at the boundary of the structure. Everything else is secondary. What we really care about is this distance. This is the width. It represents how safely the classes are separated. And this direction vector is called W. It is perpendicular to the boundary. It controls how wide the margin becomes. If we focus only on this region, everything about SPM becomes clearer. The goal is no longer just separation. The goal is to maximize this margin. Now that we know what margin is, let's find its exact width. Remember these three lines. The distant boundary sits in the middle and the support vectors lie on two margin boundaries. These are the points that matter. Everything about the optimal boundary is determined by them. Let's call the positive support vector x plus and the negative support vector x minus. The vector from one support vector to another is simply their difference. So this red vector represents displacement vector. Because these points lie exactly on the margin boundary, they satisfy special equations. The positive support vector satisfies plus 1 and the negative support vector satisfies minus 1. But we are not interested in the entire displacement vector. We only care about the part that points directly across the margin. And that's where the vector W comes in. W points perpendicular to the hyperplanes. So the margin width is simply the projection of the displacement vector onto the direction of W. That projection gives us the width between two margin boundaries. Visually, this is the exact quantity we are measuring. The total width is 2 times the width of the margin. Now we substitute the support vector condition into the equation. The bias terms cancel out and everything simplifies beautifully. The width becomes 2 divided by magnitude of W. The result is extremely important. If the magnitude of W gets larger, the margin becomes smaller. And if the magnitude of W gets smaller, the margin becomes wider. So maximizing the margin width is exactly the same as minimizing the magnitude of W. And that simple idea becomes the optimization problem at the heart of support vector machines. Let's imagine we have a perfectly separated dataset. Blue points belong to one class, green points belong to another. At first glance, the problem seems solved. There are many lines that can separate these two groups correctly. Here we can see all three lines separates the data perfectly. So once again, which one should we choose? Here's where SPM thinks differently. It doesn't just look for a separating boundary. It looks for the widest possible empty corridor between the classes. A corridor where no training points exist. The wider this corridor becomes, the more space we have before anything goes wrong. And that extra space turns out to be extremely valuable because real-world data is never perfectly clean. Measurements can contain noise. Sensors make mistakes. So let's test our boundary. Imagine these critical points shift slightly. Nothing dramatic, just a small amount of noise. The data hasn't changed much. A boundary that looked acceptable before can suddenly become fragile. This separator no longer has enough room to absorb the disturbance. The safety buffer disappears. But notice something important. The wide margin boundary survives because it started with extra space. Small changes in the data don't immediately break it. The corridor absorbs the shock. And that's exactly what we want from machine learning model. A larger margin means greater tolerance to noise. Greater tolerance to noise means better generalization. And better generalization means better prediction on data that the model has never seen before. That's why support vector machines don't just separate the classes. They maximize the width. Because more width means more safety. More margin, more safety, better generalization. That's the main principle of SPM. Now we understand something important. SPM tries to create the widest possible margin. A margin that makes the classifier more stable and more resistant to noise. But here's the surprising part. Most of the data points don't actually control the boundary. They are part of the dataset, but not part of the decision. Instead, only a few points matter. The ones closest to the margin. These are the points right at the edge. They are the first points the boundary would touch. Now imagine removing everything else. Even then, the boundary still holds its position. The margin still exists because those removed points were never controlling it. These special points have a name. They are called support vectors. And they alone define the position of the decision boundary. Without them, the classifier wouldn't exist. Now watch carefully. When a support vector moves, the entire boundary moves with it. The margin changes, the classifier reacts immediately. Now bring it back and everything returns. The same happens here. Move the support vector and the entire decision boundary changes. This shows something powerful. They control the entire model. Now what's the normal point? Even if it moves significantly, the boundary barely reacts because this point does not define the decision. So in the end, the SPM doesn't depend on all points equally. It depends only on a few critical points, the closest points to the boundary. Everything else is just a noise and those critical points are called support vectors. Now look at this again. Same data, same structure. But now you already understand it. At first, it looked completely random. Any line could separate it. But the real structure was always there, hidden in plain sight. Now look again. You already know the answer. It was never about all the points. Only a few ever mattered.